Welcome back to the Deep Dive.
All right.
Today, we're doing something a little different. We are looking at this stack of resources that claims it can map out the entire career path of a back-end engineer.
Mm-hmm.
And honestly, looking at this, we've got articles on HTTP protocols, database sharding, distributed queues. It feels a bit like trying to learn a whole new language in like 20 minutes.
It does feel that way, doesn't it? But here's the fascinating thing about the material you've pulled for today. It argues that learning the language, the actual code syntax, is the last thing you should be worrying about.
Which sounds completely backward. Usually when I want to learn something technical, I grab a tutorial, I open a text editor, and I start typing. I want to see hello world on the screen.
And that is exactly the trap this research points to. It calls it the framework trap. If you start your back-end journey by just, memorizing how to write a function in Ruby on Rails or Express.js, you're not learning back-end engineering.
You're just learning a tool.
You're learning a tool. You're learning the how before you understand the why.
Right. It's like learning to play one specific song on the piano without knowing how to read music. You can play that song great, but you can't compose anything new.
Exactly. And the mission of the source material we're diving into today is to flip that script. We are going to walk the path of a true back-end engineer. And that means starting with the philosophy, the language agnostic skills, before we ever write a single line of code.
I love that term, language agnostic. It sounds so grand.
Mm-hmm.
But basically, we're looking for the universal truths, right? The things that are true, whether you're coding in Python or Go or Java.
Precisely, because frameworks, they change every few years. The fundamental architecture of how the internet works, that stays the same.
Okay, so let's start at ground zero. The big misconception, I think a lot of people, myself included, think backend is just CRA.
Yeah.
Create, read, update, delete. You have a database, you make a little API to put stuff in and take stuff out, and you're done. Easy.
If only it were that simple. The expert insight here is pretty blunt. CRUD is just the tip of the iceberg. True backend engineering isn't about just making code that works when you test it.
On your laptop.
On your laptop, yeah. It's about building systems that are fault-tolerant, scalable, and maintainable when a million people are hitting it all at once.
So it's the difference between building a treehouse and building a skyscraper. Both have walls, but the engineering underneath is totally different.
That's a perfect analogy. And the foundation of that skyscraper starts with the request journey, phase 1, first principles.
Okay, first principles. A user clicks a button, a request flies across the internet. What is actually happening?
So we have to talk about the medium of communication, which is HTTP. And there's one core concept here that you absolutely have to grasp to understand backend: statelessness.
Statelessness. We hear this all the time. The web is stateless. But let's really unpack that. To me, it sounds like the server just has a terrible memory.
It has no memory. That's the point. Think of the server like a person who has total amnesia. Every single time you talk to them, they have no idea who you are or what you said 5 seconds ago.
So if I log in, and then 5 seconds later I try to check my profile.
The server doesn't know it's you. It doesn't remember that login.
That seems wildly inefficient.
It seems that way, but it's actually the secret to scale. Because the server has amnesia, every single request you send has to be completely self-contained. It has to carry everything. Hi, I'm user123. Here's my security badge, my token, and I want to see my profile. You have to reintroduce yourself every single time.
So we can't rely on the server remembering us. We have to be explicit. And that leads to the methods the sources talk about, the verbs.
Right. We use specific verbs to tell this amnesiac server what our intent is. We use getT when we want to fetch data. We use ppost when we want to create something new, put to update, delete to remove. These aren't just arbitrary words. They tell the server and other developers exactly what we're trying to do.
Okay, so we have the message. Now we need to know where it goes. That's routing.
And routing is just the address book. It maps a URL-like user's profile to a specific function in your code called a handler.
But here's where the research gets really interesting. It says, don't just dump all your code into that handler. It talks about this separation of concerns, architecture. Seems like every language uses it. Controller, service, repository. Why make it so complicated?
This is the pattern that saves you from what we call spaghetti code. Imagine a hotel. The handler is the receptionist.
Okay, the receptionist at the front desk.
The receptionist's job is just to greet you. Do you have a reservation? Is your credit card valid? They don't cook your food. They don't clean your room. They just validate the request and pass it on.
So the handler just checks the input.
Exactly. Then the handler passes that request to the service layer. This is the brain. This is the hotel manager. This is where the actual business logic happens. Calculate the room rate, apply the discount code, check for availability.
And the third layer, the repository.
The repository is the librarian or maybe the archivist. The service layer says, I need to know if room 202 is free. It asks the repository. The repository is the only part of your code that knows how to talk to the database. It fetches the data and hands it back.
I see. So if you ever change your database from, say, MySQL to Postgres, you only have to retrain the librarian.
Exactly.
The receptionist and the manager don't even need to know the database changed.
That's the power of this architecture. It makes your code testable, flexible. If you mash everything into one file, you can't change anything without breaking everything else.
That's a great segue into phase 2, data persistence. The database. The research asks a really fundamental question. Why do we even need a database? Why can't the server just, keep the data in a variable?
This comes down to physics, really. You have to understand the difference between RAM and disk.
RAM is primary memory, right? The super fast stuff.
Incredibly fast. But it's volatile. That means if the power flickers or the server crashes or you just restart the program to deploy an update, poof.
It's gone.
Everything in RAM is gone forever.
So if I stored my users in RAM every time I deployed a new feature, I'd delete everyone's account.
You'd have a lot of very angry users. That's why we need persistence.
Yeah.
We need to write data to the disk, the hard drive. That is secondary storage. It's slower, sure, but it survives a power outage. A database is just a very specialized tool for organizing data on that disk.
Now, for a backend engineer starting today, the source material is very opinionated. It basically says, just use PostgreSQL. Why Postgres?
It's the Swiss Army knife of databases. Historically, you had to choose. Do you want a relational database like SQL where everything is in neat tables with rows and columns? Or do you want a NoSQL database like MongoDB where you can just dump flexible JSON documents?
And you had to pick a side and live with it.
Right. But Postgres supports both. It's strictly SQL compliant, so it's reliable and relational. But it has this amazing feature called JSONB. It lets you store unstructured JSON data right inside a table, so you get structure where you need it, for user accounts, and flexibility where you want it, for user settings.
It's the best of both worlds. Okay, speaking of databases, there's one thing that terrifies every junior developer: changing the database. You need to add a new column or rename a table. The fear of breaking production it's real.
It is terrifying. And you should never, ever just log into the production server and type SQL commands to change the structure. That's cowboy coding. The solution the research highlights is database migrations.
Migrations? This is like a time machine for your database, really.
That's a great way to put it. A migration is a file. It's a script that describes the change you want to make. But the magic is that every migration has two parts: an up and a down.
Up and down.
The up command applies the change. Create the users table. The down command undoes it. Drop the users table.
So if I deploy a change and the entire website crashes?
You just run the down command. It rolls the database back to the exact state it was in 5 minutes ago.
Yeah.
It turns a potential catastrophe into a minor undo. It gives you confidence.
That safety net is huge. Okay, so we got our principles, we've got our database. Phase 3, scaling. The app is a success, but now it's slow.
The success disaster.
The sources outline 2 ways to fix this: vertical scaling and horizontal scaling. Vertical seems like the lazy way out.
It is the easy way out. Vertical scaling just means buying a bigger computer. Give me more RAM. Give me a faster CPU. It's great because you don't have to change your code, but there's a limit. You can only buy so much RAM before it becomes impossibly expensive.
And if that one supercomputer catches fire, you're done.
Exactly, a single point of failure. That's why real backend engineering aims for horizontal scaling. Instead of one giant computer, you want 10 small, cheap computers all working together.
But this brings us right back to the beginning, doesn't it? Back to statelessness.
It does. This is the aha moment. Remember our server with amnesia.
Yeah.
If you're scaling horizontally, you must respect statelessness. Imagine you have server A and server B. If I log in and server A stores my logged in status in its own RAM.
And then my very next click gets routed to server B.
Server B has no idea who you are. It can't read server A's RAM. To the user, you're suddenly logged out.
So to scale horizontally, no single server can hold any unique information.
Correct. You have to externalize the state. You put that session data in a shared database or a cache like Redis. Now, server A and server B both check Redis to see who you are. The servers become interchangeable. You can destroy 5 of them and spin up 5 new ones, and the users won't notice a thing.
That makes so much sense. Statelessness isn't just a random rule. It's the key that unlocks infinite scaling.
Precisely.
Now, scaling isn't just about adding machines. It's also about how efficient each machine is. The sources get into concurrency, and they make this distinction between I/O-bound and CPU-bound. Can we break that down?
Sure. This helps you understand why languages like Node.js are so popular. Most backend work is I/O bound. That stands for input-output.
Which just means?
It means the server is waiting. It's waiting for the database to reply. It's waiting for an external API. It's waiting for the network. It's not actually doing heavy math.
So it's like a waiter in a restaurant.
Exactly. A waiter takes your order, hands it to the kitchen, and then immediately goes to serve another table. They don't just stand there staring at the chef until the food is ready. That would be incredibly inefficient.
And that's what Node.js does with its event loop, right? It's a hyper-efficient waiter.
Yes, it can handle thousands of connections at once because it never blocks. It just takes the order and moves on. Contrast that with CPU-bound work like processing a 4K video or mining crypto. That requires the CPU to work hard constantly.
That's like the waiter having to go in the back and chop all the vegetables themselves.
Right. And if the waiter is chopping veggies, they can't take any new orders. If your app is CPU-bound, Node.js might struggle. But since 99% of web apps are just I/O-bound, these models are perfect.
Okay, speaking of heavy tasks like video processing, that leads us to phase 4, advanced systems. Sometimes you do have to do heavy work, like sending 10,000 emails. You can't just make the user wait while their browser spins.
No, the user will leave, the request will time out, you need to decouple the request from the action, you need a task queue.
So what does that look like in practice?
The user clicks send newsletter, the API says got it, and responds immediately. The user sees a success message instantly, but behind the scenes, the API hasn't sent a single email.
It's lying.
It's deferring. It created a job, a little ticket, and put it in a queue. Think of it like a line at the DMV.
Okay.
Then you have a completely separate set of servers called workers, and these workers are just watching that queue. They pick up a ticket, process the emails for that job, and then grab the next ticket.
So the website stays fast and snappy, and the heavy lifting happens in the background at its own pace.
Exactly. And if the email server goes down for a minute, the worker can just put the ticket back in the queue to try again later. It makes the whole system resilient.
Resilient and safe. We have to talk about security. The notes here have a pretty dark rule. Never trust the client.
It sounds paranoid, but it's the golden rule of backend. You have to assume that every single piece of data coming from the outside, every form, every URL parameter, is potentially malicious.
It could be a regular user making a typo, or it could be a hacker trying to break in.
Exactly. So you need layers of defense. The first is input validation. Before you even look at the logic, check the data itself. Is age actually a number? Is it a positive number? If someone sends age -5 or age, delete database, you block it at the door.
And then there's sanitization.
Especially for databases. We've all heard of SQL injection. If you take raw text from a user and paste it into a database query, you're handing them the keys to the kingdom. You have to sanitize inputs, clean them, so they're treated as just text, never as commands.
And finally, rate limiting.
Right. Don't let one IP address hit your login page 500 times a second. That's a brute force attack. You have to set limits to protect your resources.
So we've covered the philosophy, the database, the scaling, the queues, the security. We have designed a fortress. Now, phase 5, we actually have to build it. Implementation.
This is where we finally get to talk about languages. The sources highlight two main paths that dominate modern backend: Node.js and Golang.
Why those two specifically?
Node.js is the ecosystem king. It runs on JavaScript, so if you're a front-end developer, you already know the syntax. You can jump into backend almost immediately. It's fantastic for startups and for rapid prototyping.
And Go.
Golang is the language of cloud engineering. It was built by Google for their own massive scale. It's statically typed, which means fewer bugs, and it compiles to a single binary, so it's incredibly fast. If you're building high-performance microservices, Go is often the choice.
But the reassuring thing I saw in the notes is that the concepts don't change. A service layer in Node looks structurally very similar to a service layer in Go.
That's the language agnostic part coming full circle. Once you understand the architecture separation of concerns, statelessness learning the syntax of Go is just a weekend project. You aren't relearning how to build. You're just learning a new dialect.
And finally, the last step on the path, production-grade projects. The research is really emphatic about this. You can't learn this just by reading. You have to build systems that handle chaos.
Real-world chaos, yeah.
You have to start thinking about day 2 operations.
Day 2.
Day 1 is launching the code. Day 2 is keeping it alive. The sources mention graceful shutdowns.
Which sounds very polite.
It is. When you need to turn off a server to update it, you don't just pull the plug. You might be cutting someone off in the middle of a payment. A graceful shutdown means the server stops accepting new requests, finishes the work it's currently doing, and then shuts off.
And observability. You can't fix what you can't see. When your code is running on a server in a data center across the country, you can't just stare at the screen.
Yeah.
You need logs, metrics, tracing. You need to know not just that it crashed, but why. Was the database slow? Did the memory spike?
It seems like the transition from coder to engineer is really about this shift, moving from I made it work on my laptop to I made a system that can survive in the wild.
That is the perfect summary. It's shifting your thinking from writing syntax to designing systems.
It's a lot to take in, but it certainly clarifies why back-end engineering is such a distinct and deep career path. It's not just the plumbing, it's the architecture of the entire building.
Absolutely. And if I can leave our listeners with one final provocative thought from the material, it's this.
Let's hear it.
The next time you write a line of code, stop looking at the text editor for a second. Close your eyes and try to visualize the physical reality of that data. Ask yourself, where does this actually live? Is it in the fleeting electricity of RAM? Is it etched onto a spinning magnetic disk in a server farm in Virginia? And then ask yourself, what happens to my entire system if that disk just disappears right now?
That is a haunting question. But I think it's the question that separates the amateurs from the pros. Thinking in systems, not just in code.
Exactly.
Well, that wraps up our deep dive into the path of a back-end engineer. A massive topic, but hopefully the roadmap is a little clearer now. Thanks for listening, and we'll catch you in the next deep dive.